Okay, so I'm sorry for the inconvenience. Hopefully now everything is working, have been working nicely. So first let me know if you can hear me well and if you can read the board. And then we can discuss a little bit what we did in our theory lectures and about these exercises. So first thing is, do you have questions about LAG 6 or 4? Well, question about LAG 5 or 6 maybe. So there any question about what we did in these two? A few minutes for you to think. Okay, so if you don't have questions about these, I just want to make a point with a proposition in the notes about the determinant, about 3x3 determinants, in which we give a very special interpretation. So suppose you have these three vectors, u, v, and w, and we write them in components. So uxi, uyj, uzk, vxi plus vyj plus vzk, and wxi plus wyj plus wzk. Using these components, you see we have 9 of these, 3, and then we have other 3, other 3. It is pretty natural to organize them as the rows of a matrix 3 by 3. And since this matrix is square, I can compute its determinant. So I can compute these 3 by 3 determinant either using Sarus rule or using the recursive definition we saw yesterday. And what is the catch here? What is interesting? Well, that the number I obtain computing this determinant is nothing more than the cross product, the mixed product of the vectors. Okay, so the determinant you compute it this way is nothing more than the cross product of these vectors. And these you can see very well by, oh, sorry, copy. This is W, Wx, Wy, Wz. And these you can see pretty well by using the recursive definition of determinant we saw as last thing yesterday, right? So one way of seeing this is that if you want to compute, so this is just a chit chat, if you want to compute this cross product, basically you are looking at this table and you compute the 2 by 2 determinants. And then you multiply those by numbers, right? So if you think at what we did yesterday, it is very natural, I hope, to see that u dot v cross w is exactly this determinant. So let's make it like this. Then remove these, remove that. This is equal, and you can see it immediately by using the definition, right? Because when you compute the cross product, you use this determinant by 2 by 2 by this number minus this number times the determinant 2 by 2 plus this number times the determinant 2 by 2. And the fact is that if you remember about property of the cross product, when you shift vectors around, the operation will not change, right? So when you shift vector around, the result of the cross product is the volume always, but having the same sign. So this could be an idea to see why what is in the proposition is true. And it is basically just a computation, okay? Good. Someone says, is it easier to compute the cross product? And then it is exactly the same amount of operation. Sayed Mustafa Sayedi, if you think about it, computing the cross product is computing the three 2 by 2 determinants, and then you have to compute the dot product. Is exactly the same amount of work. So is exactly the same amount of computation you have to perform to obtain that result. Yeah. Well, you can do the dot product first if you exchange these two. Well, sorry, dot product first you cannot do. You can do the cross product first. So maybe I misread. I thought that U star V was the cross product. So first is the cross product, then the dot product. So if I misunderstood, I'm sorry in explaining this. Okay, good. Multiplying them in one step is computing the determinant. Mahmoud El-Kolali, yeah, is exactly computing the determinant. This is what the determinant will do for us. Okay, so if you don't have questions about what is contained in the lecture notes, what we'll do is move to the exercise part. So let's do that. And we start looking at the exercises I told you to have a look at, but the file was not there, so maybe you didn't have a lot of time. So for example, the first one is giving us the task of computing, I would say, AB transpose and B transpose, A transpose in some cases. So let's say when we have two cases. Case 1, A is 1, 2, 3, and B is 1, 0, minus 1 transpose. And second case is when A is, again, 1, 2, 3, but now is transpose, and B is 1, 0, minus 1. So we want to compute these two, okay? So let's see how we can compute this. Yes, thank you for giving me the idea here. It is ATBT, yeah. But let's say we want also to compute BTAT. So this is a new kind of exercise. But what is our point is that we want to practice a little bit of computation. So what happens in the first case? Let's say this one. So what happens in this case? Case 1. So when I compute A times B, what kind of matrix do I produce? What size is this matrix? Exactly. One say Cesare Piemontese and other people, they say 1 by 1, because they multiply a 1 times 3, and the transpose of a 1 times 3 is a 3 times 1. So the result is going to be a 1 times 1 matrix, so it's just a number. And what number is this? Well, it is the product 1 to 3 times 1, 0, minus 1. And I hope you recognize this as the dot product of these two vectors, right? Exactly. And so what is the answer? Is going to be 1 times 1 plus 2 times 0 plus 3 times minus 1. And so we will get, between parentheses, because it is a matrix, 1 plus minus 3. So we'll get number minus 2. Okay, so this is the computation we made here. Then what can we compute else? Can we compute can we compute B times A? So what do we get for B times A? What do you think? The question of Ash Bairaji. Well, the product of matrices is a matrix. So this is a 1 times 1 matrix. Yeah. So about computing B times A, can we do that? Maybe we cannot do that. How do we decide? Well, this is a 3 times 1 times a 1 times 3. So yes, I can compute, right? Because the middle one are equal. And the size, Alberto Eusebio, yeah, you are correct, is going to be a 3 by 3 matrix that I compute as 1 to 3 times 1, 0, minus 1. And now let's perform the computation using the definition. Just for the first time we do this, you have to multiply row by column. So if I want to obtain the first result here, what do? I multiply this number by this row. So I will see 1, 0, minus 1. When I do the second row, I will multiply this number here. No, it's unreadable. This number here, say, by the same row. So I will get 2, 0, minus 2. And finally, you will get 3, 0, minus 3. So I hope you see that all the rows are multiple of the same row, okay? All rows, so all rows are multiples of B, sorry, A, the row vector, right? And also, if you check it, if you check about this, you will see, oh, thank you. You are saying that I mix up the numbers. Thank you. Thank you for letting me know it. It will be quick to change. Thanks. So it is 1. So let me check here. Okay, so it was too quick what I said. Let's go backward for a second. So what about B? B is 1 times 3. Now I see what you said when you wrote in the chat. And this is 3 times 1. And then you were correct. This is 1, 0, minus 1. Multiply A, which is 1. Oh, no, but I'm reading the wrong line. Sorry. My bad. So I was reading line 2. So let's go back to line 1. So this is going to be the 1, 0, minus 1 times 1, 2, 3. Yep, sorry. Well, I will not repeat the computation because now we understood what happens. All rows are going to be multiple of the green one, the second one. So I get 1, 2, 3, 0, 0, 0, minus 1, minus 2, minus 3. Now it is correct, right? Because I was looking at the wrong row. Thank you for letting me note this. Okay, now it should be clear, right? Thank you. Also, all columns are multiple of what column? Well, this one. You see, this column here, this column there, and this column there are all multiple of the same column. Okay, so the resulting matrix BA is done by multiplying either the rows or the columns by the number given by the other one. This is a kind of neat way of putting them together and make them work. Yeah, thanks. And now let's say I want to compute with transposes. So let's say this is an extra thing we want to have a look at. What is going to be A, B transpose? Well, this is easy. This is just minus 2 transpose. So it's just minus 2. Nothing is going to change. And now I would like to compare this with B transpose, A transpose. Okay, so I'd like to compare this with 1, 0, minus 1, and 1, 2, 3. But since we know this is the dot product, this is clearly not going to change. So the small remark is that, look, these two are equal. AB transpose, B transpose, A transpose, well, they are equal, okay? Similarly, I could play the same game and say, well, what is BA transpose? Well, it is just the transpose of the big matrix here. 3, 0, minus 3 transpose. And so it is 1, 2, 3, 0, 0, 0, minus 1, minus 2, minus 3. Not a big change of setting. And now what is B transpose? A transpose? Well, let's try, sorry. And what is, now I want to compare with A transpose, B transpose. So what is A transpose? Well, this is matrix A, so it's the one I did by mistake before, right? So 1, 2, 3, and this is matrix B transpose 1, 0, minus 1. Now, if you compute this, what do you get? Well, we know that the rows are going to be multiple of this one using these numbers. So what we get is 1, 0, minus 1, 2, 0, minus 2, 3, 0, minus 3. So this is how you get the result, right? And again, they are equal. So there is a subspecies here. Salvatore Orlando is the last one making this guess. So let's see it as a guess. So we have a guess. And our guess is that, well, if you compute AB, and you can compute it, then when you transpose it, it's going to be B transpose, A transpose. So it is like saying when you compute the transpose of a product, you are computing the product of the transposes in reverse order. And what Salvatore Orlando wrote is that if you take the transpose, transpose, take transpose, what you will get here is going to be BA, because you take the transpose twice, and we already know that taking the transpose twice just change nothing. It leaves the BA, okay? So what is important is to see if this is true, because this, for example, would imply what is downstairs, right? Okay, So the first reality check about this is about dimensions. Let's make a dimension check. If I compute AB, so if I compute this product, this means my matrix is something like n times P. This is matrix A, and this is P times M. And the resulting matrix is going to be n times M. So when I compute B transpose, this is going to be a P times M matrix. And A transpose is going to be, when I compute B transpose, this is going to be a M times P matrix because I exchange, right? When I compute A transpose, this is going to be P times N. And so the resulting matrix D is going to be M times N. So, of course, these two cannot be equal because they have different size. But it is possible, and this is part of our guess, that I can go from one to the other by transposition because I exchange rows and columns. So the dimension check is okay. So the formula in the gray box could be true because AB transpose has the same size dimension of B transpose A transpose. Okay, so now the next exercise 3.2 well basically ask us to prove that the guess is true. So AB transpose is B transpose A transpose. So this is what the exercise asked me to do, to prove that I can do this. Okay. And there is a very nice way of doing this that will basically use this approach, computing AB and comparing B transpose A transpose with the transpose of AB. And I suggest we do in the following way because it's a way for us to recall quite a lot of things. So say I want to compute A times B. Remember, when you have a matrix and say these are the sizes we are looking at, when you have a matrix, I can see it as a collection of rows. So row 1, row n, or a collection of columns, C1, Cm. And just note that row, these Ri and these Cj have the same dimension, which is P. So when I compute the product of this matrix, who's going to be in position 1, 1, for example? Can you tell me who's going to be the number in position 1, 1? R1, C1, yes. And then it will be R2, C2 in position 2, 1, R1, C2 in position 1, 2. I can go all the way down, R1, Cm, right? All the way down, I will have Rn, C1. And in the corner, I will have RNCM. Okay? Of course, it is, thank you, Sophia Karnauk, R2C1, because R2C2 is here. Thank you very much. Yep. Okay, good. So this is A times B, this part. Now let's have a look to B transpose, A transpose, okay? And now you tell me, what is the best way to write B transpose if I want to play this game? What are the rows of B transpose? Alberto Eusebio, yes, you are correct. The rows of B transpose are the columns of B. So here I will write C1 transpose, right? Because C1 is a column, and now I want a row. And all the way down, CM transpose. And similarly, what are the columns of A transpose? Well, you probably know by now. They are going to be the rows of A transpose. So this is row 1 transpose, all the way, row N transpose. Okay, so now I compute the product here. And I have C1 transpose, R1 transpose, C1 transpose, R2 transpose. And for example, here I have C2 transpose, R1 transpose. And in the corner, I will have CM transpose, RN transpose, right? Okay. And so what do we do at this point? Well, we have to compare these two objects. And what I want to see is that the transposition of one gives me the other, right? Okay, so let's now compute AB transpose. So let's do this. So what is AB transpose? Well, AB transpose will be the matrix I get from this one here, which I will now copy. I will now copy. And by the way, this transpose is outside, of course. So now I want to compute the transpose of these matrix here, which I do by exchanging elements in symmetric places. So for example, this element here goes in this place. So this is R1, C2. And here I will have R2, C1. All the way down, I will have then R1, Cm. And all the way down here, I will have Rn, C1. And in the corner, I will always keep Rn, Cm. Okay? Good. So now let's think for a second and compare these element here, R1, C2. So row R1, column C2 is a number. And now I want to compare it with this element here, which is the transpose of C2. So, oh, sorry, I'm too quick today. So let's do this again. R1, C2 is row R1, column C2, dot product. I want to compare it with C2 transpose, R1 transpose. So I want to compare it with C2 transpose, which is now sit like this, and R1 transpose, which is now standing like that. And remember, these two are just dot products. Right? They are just dot products of vectors. And so they are equal. Because what do? You take the first component, you multiply by the first component, second component, and you take the sum. And here you do the same thing by exchanging the components. So these two are equal. Okay, so just let me know if you agree that these two are equal. And if you agree, then all the elements in the in the AB transpose and the BA transpose are equal, and we are done, because remember, this second line is B transpose A transpose. And so we proved these two are equal always. Okay? Okay, any question about this? Very well, very nice remark, Giancarlo Sordones Herrera. Yes, these equal sign here, and so these equal sign there, simply hold because of that. Yeah, you see how we use a lot of basic properties, because if you have x1, xn, and you multiply y1, yn, what you get is the number of metrics, depending on your interpretation, is the sum of xi, yi, I from 1 to n. And if I multiply y1, yn, x1, xn, what do I get is the sum I equal 1 to n of yi, xi. And these two are equal because each single summand is equal. And this is because in real numbers, the product is commutative. So I hope you start appreciating now that commutativity, which is something you probably have always taken for granted, natural, assumed, it is not so trivial, but it is very important. And it plays a role even when dealing with matrices for which the product is not commutative, right? The product is not commutative, but playing with real numbers, we can obtain interesting properties. Amos Lanzuisi, yes, basically, this note comes from here. Why is this equal? So imagine C2 transpose is this one, and R1 transpose is this one. When you do the other one, you are just exchanging the role of Y and X. When you compute this dot product, you are computing this summation, first times first, second times second, and so on. When you exchange the role, you are just exchanging the order in the real number or complex number multiplication. So if you do that, right? So if you do that, what you get is the explanation of why the multiplication of matrices satisfies this property here, that the transpose of the product is the product of the transposes in the reverse order. I think we'll do 311. Who is asking? Riccardo Gianni. Let's do like this. It's probably a good idea. We can see it now. Just let's remind what inverse means and about invertible. And then, yes, we can do 311, and then we go back to 3.4. So let's make a note. Remember, a n times n, so square, only square matrices here, is invertible if and only if there exists a minus 1 n times n such that two things happens. A minus 1 is the inverse of the proper size, and this is also true when you reverse the order of the factors, right? So this is the definition of invertible matrix. This is the definition of inverse. So it is invertible if and only if the inverse exists. By the way, if it exists, the inverse is unique. That will be a nice thing for you to try and understand. So I'll do like this. I leave it to you. So let's say it's for you to try. So try. If the inverse exists, sorry, if A inverse exists, then it is unique. And so we can speak about the inverse. So try yourself with this, and then you let me know if you manage. Don't now. Okay, now let's follow the general argument. Try it in your, idle time, and then we'll see. Okay. 3.11 says something like this. Basically says to ask to prove that A minus 1, so it means that A is invertible. If I take the transpose of this matrix, this has something to do with the transpose of the inverse. Well, the inverse of the transpose, sorry. These two are equal. Okay, so what does it mean for in order to prove this? Well, in order to prove this, so you want to see basically that this matrix here is the inverse of the transpose. And this is also proving that if A is invertible, also the transpose is invertible. So how can we do this? Well, what you have to do is to ask yourself, what is the product of A transpose times A transpose inverse? So this is what you want to compute. Okay, so this is what you want to compute. And you want to show that this is equal to the identity, right? I'm reading in the chat, there is one thing I don't understand. Samezun Singh says, yes, diagonal matrix. Maybe you were answering someone else's question, so I don't see it well. Paolo Lovera said it means -1 is equal t. This is a little bit scary in some sense. It means that transposition and inverse compute. So this means that transposition and inverse commute. So it's not important which one you do first. You can compute the inverse of the transpose or the transpose of the inverse, and the result will be the same. You see, you can compute the transpose of the inverse or the inverse of the transpose, and the result will be the same. So what you want to show is that the transpose inverted is equal to the transpose of the inverse. So how do you prove it? Well, I'll do this. So as many of you said, this is equal to IN by definition. Alberto Eusebio said that. Then I use what I have written here. So what I have is that at minus 1, I want to see what is a minus 1 times t, right? If I prove that this is equal, so if I prove that this product is equal to the inverse, I prove that this is equal to that, right? This is what we need to prove. This is what we know. The inverse of a matrix times the matrix gives the identity. Now I ask myself, what is this? And this you can compute using the property we saw before. This is a minus 1 times a all transpose. And this is so the transpose of the identity. So maybe now I understand what Samyung Singh said, that the transposition of the identity is equal to the identity because it is a diagonal matrix. Okay, so you see, what we got is that this product is equal to the identity. And similarly, you can also prove that a minus 1 transpose times a transpose is equal to the identity too. So you can also prove this is the same approach. And so these two things together tell me that a minus 1 transpose is the inverse of the transpose because it multiplies the transpose of left and right into the identity. Yep. So Samyung Singh was saying that since this is a diagonal matrix, when you take a transpose, nothing is going to change. That's true. And that's how you prove these 3.11. We can make a note about this identity here. So let's make a note. So a matrix such that A transpose is equal A, like in this case here, is called symmetric. So question for you, let's see what you think. Can a can a non-square metric be symmetric? So can a 2x3 matrix be symmetric? Yeah, it's not possible because the sizes will not match, right? So if A is n times m, this is m times n. If they are equal, it must be n equal m, right? That's necessary. So it must be that the matrix is square. Yes, Cesare Piemontese, when you take the transpose of a matrix, what is on the diagonal stay fixed when it is square. Yeah, that's perfectly true. And if you want examples of square matrices, which are of symmetric matrices, which are, let's do it again. So diagonal matrices are symmetric. So diagonal means symmetric, but there are also matrices which are not diagonal, but are symmetric anyway, right? So symmetric basically means that when you take off diagonal elements, they are equal. It's just that. And the diagonal can do everything you want. So if you have all zeros outside the diagonal, it is automatically symmetric. You can have it symmetric even if you don't have only 0 outside the diagonal. Okay. Now let's go back to the other exercises if you don't have special questions, remarks, or doubts. The zero matrix is symmetric. Yes, because the transpose of 0 is 0. Giancarlo Herrera, you are correct. Yeah, that's true. The transpose of the zero matrix, when it is square, the square zero matrix, n times n, it is true. Yeah. Okay, now something very simple. Let's take a matrix A like this. A is a real number, and then we ask two things. Compute all A such that A is invertible. And then when A is invertible, compute A minus 1. Okay, so you probably had time to think about this before. So for what values of A is A invertible? What are the values of A making A invertible? What do you think? So the matrix is invertible when A is equal plus minus 1. Are you sure, Erfan Kar? When they are different, yes. Okay, good. But how do you answer this question? Well, simply you do this. You say, well, I can find the inverse if and only if the determinant of A is not 0. This is what we learned last lecture. And this is 1 minus A squared, which must be different from 0. So you can find the inverse if and only if A is different from 1 and A is different from minus 1. So this means that, for example, for A equal 1, this matrix here is not invertible. And for A equal minus 1, this matrix here is not invertible. And you can see they are not invertible by playing the game we played during the lecture. I just show you how you can do that. You multiply this by 1 minus 1, you get 0, 0. So if the inverse existed, you will get a contradiction. This vector equals 0, right? And then you say, if you can find A minus 1, then you find a contradiction that these two are equal. Try to repeat the argument if you don't remember, but this is not what the exercise asked. The exercise asked for what values of A is invertible, A not 1, A not minus 1, and then we want to compute the inverse. To compute the inverse, it is just a matter of using the formula, say, because the formula tells me that A minus 1 is equal 1 over the determinant. And then I have to perform the computation. So I write A here for a second. So if you remember, you have to put the diagonal elements exchange, and then the off diagonal elements exchange with a minus in front of them. And this is the inverse of our matrix A. And I encourage you to compute the inverse. Writing A minus 1 is equal 1 over A, well, it's not very useful Samason thing. You need to be able to compute it. And you don't compute it by taking the reciprocal of the elements. You compute it by applying one of the rules. For the time being, we only have one rule for computing the inverse, and then over 2 by 2. And so we apply it. Okay, good. Do you have any question about this? So if you don't have any special question, I suggest to you a new exercise. Let's see, which is here. So I take the same kind of thing, but I change the matrix a little bit. So I make it something like 1A, and then we have something like A square, A square. So let's see what are the values of A for which this is invertible. And for those values of A, let's compute the inverse. Let's see what you can do. Okay, so let's speak about these. Yes. Okay, people say it's not possible. Well, so I think your answer is that there exist no values of A for which this is true. And so we cannot compute the inverse. What is the point here? Is that the determinant of A, which we compute with the formula, product of diagonal elements, so A squared minus product of the anti-diagonal elements minus A squared is 0. And so it is never invertible because our lemma says that the inverse exists if and only if I can find a non-zero determinant, right? Erfan Kurushfar, these matrices are called singular. Singular matrices are those for which the inverse does not exist. Yep, this is the notion of invertible singular matrix. Yeah. Okay, so the other one which I suggested to you, if you don't have questions about what we did up to now, is 3.a, which has two parts. If you look at about it, it says that if a to power n equals 0 for some n, then A is not invertible. And 2, it says that if AB equal 0, then either A is not invertible, or B is not invertible. So how would you deal with the first one? Well, of course, one can say, I take the zero matrix. This is always equal to 0, so it's not invertible, period. Well, this is saying something different, because there are matrices which have this property, which are not the zero matrix. For example, you can take a matrix like this, and you see, if you compute A square, you will get the zero matrix, okay? And there are matrices that require higher powers, but what do you think about these matrices not being invertible? So why do you think these matrix is not invertible? Well, Francesca Zappula says the determinant is 0. Well, but why should it be 0? It is true for this example, but maybe there is another matrix having a power which is 0. And how can you tell that for sure that the determinant is 0 with the tools we have now? So with the tools we have now, I suggest you to say to do the following. Assume by contradiction that you can find the inverse. Then what can you do? What can you do? For example, even in this case here, we know this is not invertible because the determinant is 0, but suppose it is invertible. Then what can you do with A squared? Can you find the inverse of A squared? Can you find the inverse of A squared if A is invertible? Yep, but can you find the inverse of A squared using the inverse of A? If it exists, we are assuming it. So what would you do? So let me try this way. What happens if I multiply A minus 1 squared by A squared? Well, it means I do A minus 1 times A minus 1 times A times A. What do you get here? I will get the identity here. So I will get A minus 1 A, and so I will get the identity, right? So this means that A minus 1 square is the inverse of a square. Or in general, a minus 1 to power n is the inverse of a n. So if a n is equal to 0, then a n to power minus 1 a n is equal to 0 because it's written here, right? But it is also written here that a minus 1 to the n is equal to the inverse of a minus 1. And so here, what I get is the identity, which is not equal 0, right? So if you have that this matrix A having power equals 0 was invertible, then you would be in trouble because you would get that the 0 matrix is equal to the identity matrix. Okay? Okay. Do you have any question about our lecture of today, about exercises or the theory part? Yes, the conclusion is that, you see, if you have your matrix, let's see, having a power 0, but the inverse exists, I can multiply this matrix AN by its inverse. So it is the identity, because I proved that the inverse exists by the green statement. But when I multiply 0 by anything, I get 0. So you get the contradiction, IN equals 0. And this is the contradiction, right? Okay, so this is what gives us trouble. And Samsung Singh, yes, what you do about part 2 is it is the way of doing part 2. So Samsung Singh says, well, if AB is equal to 0, then what we get is that you don't have A minus 1 or you don't have B minus 1. And you prove this by contradiction. So by contradiction, assume A minus 1 exists and B minus 1 exists. Then the idea is that AB inverse is B inverse A minus 1 inverse. Because if I multiply this one by AB, I hope you agree, you get the identity matrix here. So you get B minus 1B, and so you get the identity again. Okay, so this equality is proved by what we wrote here. And so if you have the inverse of A and the inverse of B, you have the inverse of AB, and so you have the inverse of the 0 matrix, which does not exist. Okay? Or if you prefer, it is as before. You multiply these by B minus 1, A minus 1, you get identity to the left, 0 matrix to the right, and so you get that it does not exist. Jorge Balmaceda, how do you recommend approaching the recommended books? Well, there are a lot of exercise books that are good for you to try, multiple choices exercises, so you can practice. And there are some theory books that if you want to use because you think you need some extra, material or references, you go and have a look to them, and that's perfectly fine to me. So it has to be a adult approach, I would say. So you can do as you prefer. From my point of view, the notes, lectures are more than enough. But a book can be useful, and there are suggested books if you have no idea what book to go and look for. Il Max de Gufira, can we solve the exam book too? Well, of course, you cannot do everything there. If you want to practice solving, you go on the exercise platform. There are exercises which are topic by topic, and you can solve what we cover up to now. If you go in the book, you can probably solve 2 or 3 questions for each version. It will take longer to cover all the material, of course. Okay, good. If you don't have further questions, let's meet again next week. And please remember the tutors, they are there to answer your questions. Please go and take advantage of their service. Can be very, very useful. Okay, bye.